Welcome back, class, and I hope you're excited for our next topic, which is the beverage for all occasions, be it a breakup or a celebration. So we're going to talk about beer. So what is beer? Okay, beer is an alcoholic beverage made by brewing and fermentation from cereals. I hope you remember our cereals, and those are usually grains, and for beer it's usually malt or barley. And you add hops. Hops is another kind of plant which is being added to the beer to give it its certain flavor. So, well, technically, we could say beer could be made from plants. There are two major steps in producing your beer. First one is controlled germination or malting, and the second one is fermentation. So this is the more detailed diagram of that. We're not going to discuss this anymore, but just for you to have an understanding of the beer process. Obviously, we know beer is fermented. So the malt is being ground, and there are a lot of digesters here. You add hops, okay? You boil them, they mature, whatever. You add yeast after then. You add yeast. The yeast will be the one responsible for fermentation. Then you ferment them, and then you separate the yeast. After the yeast is fermented, you discard the yeast, and you're left with the beer, and then further processing, and finally storage and filling. By the way, let me just share some info. In Australia, there's just one, there's actually one master's degree for beer packaging. Okay, it's like packaging, but just specific for beer. So how cool is that? Okay, so how does our beer deteriorate, or what are the index of failure? So it's just actually one very big index of failure, and that would be oxidation. So oxidation causes off flavors and off odors in our beer. So oxidation, as we all know already, is accelerated by light. Then we also have effect of metal ions, and of course temperature or heat. Now, where does O2 come from in the first place? Okay, in our beer. So of course, our beer, because they are brewed there, they actually have consumed oxygen during the fermentation process. However, there would sometimes be residual oxygen still left in the beer. Now, other than that residual oxygen in the beer itself, oxygen can also find its way into the beer from three sources. Number one is from oxygen in the package head space. So if there's air inside your bottle or packaging, of course, that is a source of oxygen. Second is the permeation of oxygen through the closure. And third is the permeation of oxygen through the packaging material. Since we're dealing with liquids here, our closure choice is very important because of certain conditions like this one, permeation. Another thing, beer is sensitive to light, especially in the 350 to 500 nanometer range. If you're going to look at that in the light spectrum, that's the green, okay, yellow to green, I think, the yellow to green wavelength of light. So therefore, if you're using clear and green glass bottles, it actually allows this wavelength of light to penetrate, and thus it will react, or it will cause certain off flavors in our beer. Therefore, it is not recommended to package beer in green or clear bottles. So that's why most of our packaging for beer would be the brown ones. Okay. Of course, I'm very familiar with other beer packaging which is transparent. So the question there is if that is real beer. And the second question there is if you could also use antioxidants. Even though the packaging is transparent, there are still some ways to be able to combat the effect of light. Okay. So the major oxidative deterioration is the oxidation of linoleic acid in beer, which gives it a cardboard-like flavor. For those of you who are drinking, I'm not sure if you have already tasted the cardboard-like flavor, but if you did, then here's the explanation. Oxidation of linoleic acid. So another consideration is sorption. Although oxidation is our main index of failure, we still have to consider sorption as well, where flavor compounds are again absorbed by the packaging, which could result to a loss of hop flavor. And owing to its low pH, it's about 4.0, microbial degradation is not usually a problem with beer. So compared to our other beverage products, we don't really much care about microbes because they don't really survive here. Plus, pasteurization excludes wild yeast that could thrive. Now let's talk about the packaging for beer. Of course, like with all our beverages, we could all agree that glass would still be one of the best packaging. So the traditional packaging for beer is actually glass bottles filled with crown cork. So 355 ml volume is the most common. It's pasteurized to around 10 PUs. By the way, we have a new unit here. PU means pasteurization unit. It's equivalent to heating at 60 degrees Celsius for 60 seconds. So that's 10 PUs. So the crown cork, okay, which is used for our beer, is made of tin plate or ECCS, so electrolytic chrome coated steel, with a lining which is usually PVC or HDPE and laminated with aluminum. So again, since one of the ways oxygen can come in and out of the packaging is through the closure, okay, then you have to consider really the closure. The glass bottle itself is already impermeable, so the only way oxygen could come in and out would be the closure. Sometimes O2 absorbers are also being used. Okay, so here's okay, it's just repeated. So here's some picture here which is very timely for our pandemic from a particular picture of a beer packaged in glass bottle with the brand name Corona, and there's something extra with it. Okay, here are more examples of beer in glass. This one I'm not sure if it's really glass. Okay, it looks like it. The third picture looks like PET or some kind of very clear plastic, which is just trying to mimic the feel and look of glass. But well, we could not tell from the picture itself. But I think so. We cannot. Yeah, I think so. Okay, let's proceed. Next material used for packaging of beer is metal. So the first successful canning, sorry, wrong spelling, canning of beer took place in 1933 in Newark, New Jersey. So in 1935, Kruger's Finest started selling canned beer. So here's one example of how it looks before. I'm not sure if this is the first packaging, but it's of old packaging. Okay, with all its 1930s graphics design. So the greatest problem was the pickup of tin metal ions in three-piece cans. So since metal is, not really that compatible, especially with a lot of liquid products, that's its greatest problem, which resulted to metallic flavors or onset of haze or metal turbidity. So of course, that was the metal before. Right now, we have a lot of coatings, and the solution is actually an epoxy phenolic resin lining on the inside of our metal to protect it or separate the product from the material. Later on, three-piece aluminum cans were later released. I think in your book, there's more history notes there, but it's just a summary. So three-piece aluminum cans were later released, and then later on, two-piece aluminum cans were brought into the market, which is the more common right now. Of course, we also look at the convenience function. So previously, okay, there is no easy open end, as you could notice, okay. So before the easy open ends, we have your church key. It looks like this is the church key, okay, and you open it like that. And finally, you had your pull tab or ring pull tab or your easy open ends, and you could enjoy your beer anytime, anywhere. Here's another picture. So this is a thermochromic packaging, okay? Rather a packaging which uses thermochromic inks. The ink, the mountain here would actually turn blue if it is cold enough. So if you enjoy your beer cold you enjoy your beer cold, it will turn blue. If it's not blue, then it's not yet that cold. So that's one. Okay. This is also, we have a lot of this kind of thermochromic application. This is just the only one I have presented here in our lessons, but even in glass bottles and other products, they're also being used. Next material, let's talk about plastic, beer in plastic. So the end of shelf life for beer is when oxygen ingress exceeds 500 parts per billion, or the carbon dioxide gas egress, so egress is the opposite of ingress, is about 10%. So a monolayer PET bottle will only last 3 weeks before it reaches these limits. That will be the end of the shelf life. So 3 weeks is not enough. So to overcome this, a lot of studies actually, it's not easy to just put any product in a PET bottle. Okay, you might be wondering, why is there no PET bottle, no beer in PET bottle, or no wine in PET bottle? There is now, but it actually took a lot of study. So like this one, okay, like the limits. So to overcome this, in order to increase the shelf life, sometimes these are the following. Okay, it's not sometimes. Or these are the following studies that has been done and has been tested. So number one would be using amorphous carbon coating on the inside of your bottle. Number two is to use silicon oxide on either inside or outside. So I hope you're familiar with this already. Similar to glass, it's like glass coating. And there's another study wherein they use O2 absorbers in the middle layer. So all of them, okay, the coatings are there in order to prevent O2 ingress and CO2 egress. So this will be pictures of beer in plastic. So our last topic would now be wine. So I will see you on our last video.